All right, so let me jump over to Matlab and let me go through these projections, some code um, uh, on how to generate projections and how to reconstruct those projections, how to generate projections, then generate sinograms from those projections, then how to reconstruct those sinograms, okay? So in this code, I just make a very simple image, okay? And I use this with this circ function, okay? The circ function basically creates a white dot, like you see here, on a 512 by 512 background. So this is 512 by 512 background. And it puts the center of that 9 pixel, I think that might be the radius or the diameter, 9 pixels at these coordinates, row 128, column 128. So here, 0, 0 is up in the upper left-hand corner. If you go to row 128 and go over to column 128, it puts it right there, okay? I can make it bigger if I change this to 20. This, like I said, this is either the radius or the diameter, okay? So I just made that one a little bit bigger, like that, okay? And to do a projection, you know, what you might try to do by hand at a later time is try to make the projections by hand of this image, of this object, for different angles at theta equals 0, 45, 90, 180, and see, and then try to make the sinogram from it. Try doing that by hand. But right now we'll skip that, and I'll show you how it's done on the computer, okay? So in Matlab, you can create the projection calling the radon function, okay? So the radon function is going to return the projection intensity is capital R, and then the S detector locations as XP, okay? So if I run these two lines of code, press F9, okay, I get this, okay? This is the projection of this at theta equal to 0, okay? So you should have been able to draw that, and it should make sense. Remember, the middle of the image is where S equals 0. Going to the left, it's negative. Going to the right is positive, right? So if we look at here's the S detector axis, in the middle is 0. We do expect the projection of this to show up on the negative side, right? Right about here. Everywhere else where there's no object, the intensity is 0 because it's not going through any thickness or any linear density. But as soon as it starts to hit the circular object, it produces this shape because the chord length or the thickness of the object gets thicker in the middle of it, and then it comes back down, right? So that's the projection at theta equal to 0. Now let's try theta equal to 45, okay? And just real quick, what do you guys think? Here's our image. At theta equal to 45, where should the center of our projection line up with on the S detector axis? What do you guys think? At 0, very good. That's exactly right. Let's actually take a look at that, okay? So I'll run this, the projection, okay? I'll bring up the image of the object, and exactly right. The projection lines up at 0 because at theta equal to 45, the S detector axis is lined up like this. And now it lines up at 0. And if we keep going at theta equal to 90, okay, you'll see that that projection now shifts over to the right-hand side, okay? And that should make sense as well, because now the S detectors line up on this side, X-rays come in this direction, and so now it's showing up on the positive side. Okay, and again, the idea is to be able to reconstruct a map without cutting this object open, and we can do it by taking multiple projections at multiple angles. We can nail down exactly where that object is. Okay, and so now we know this object is in the upper left-hand quadrant. We could even know the exact coordinates of where it's located. Okay, so now I'll create the full sinogram. Okay, so I'm going to generate projections for theta going from 0 all the way to 359. That's 360 degrees all the way around. Okay, so I'll go ahead and do that and plot it. We gotta run theta. Okay, and this is what the sinogram would look like. Okay, so remember, the sinogram is plotting theta versus the S detectors. So you take each projection and line them up, and you can see the projection does start out on the negative side. At theta equal to 45, it does end up right in the middle over 0, and then it goes to the negative side as we continue rotating around the object. Okay, and so it looks like this. So this is the sinogram. This is how you can make some projections and make some sinograms in Matlab. And that was, again, for a very simple object. Let's try making something a little bit more complex. So basically what I'm going to do is I'm going to make multiple circles, and then I'm going to add them all together. Okay, so again, I just made 1, 2, 3, and there's 3 different objects, and I've added them all together so they're in a single image. And let's take a look at, again, the projections at theta equal to 0 degrees. Let's start with theta equal to 0. Okay, the projection would look like this. Okay, so we have this object here, okay, and at theta equal to 0, the projection ends up looking like this. It's bigger right here because it has to go through more, and it gets smaller because it's going through, the thickness is less, okay? And I could continue doing that for theta equal to 45 degrees. Okay, and at 45 degrees, look, I get 3 different projections. And that should make sense because at 45, they're all kind of close to 0. Now at 90, I should get 3 separate looking objects, and they should be even spread farther apart. Let's try that. Okay, look at that. Those 3 projections are spread even farther apart, and that should make sense at 90 degrees. Okay, so again, by taking multiple projections all the way around the object, we can reconstruct the map of the internal geometry. Okay, so let's go ahead and create the full sinogram of that those 3 objects. And let's take a look at what that would look like. Okay. All right. So here's the sinogram of bring up that object. Here it is. Okay. So here's the sinogram of this 3 different objects. I think we've already talked about this sinogram. I used this sinogram in a previous example. And okay, and so we've already kind of gone through this. At theta equal to 0, they all kind of overlap. But at theta equal to 90, they're spread out, and you can tell which one belongs to which object, because at 90 degrees, this one gets thicker, and it ends up on the negative side, This one gets kind of remains the same shape, narrow, but ends up on the positive side. I might have flipped that. And so you could start putting together, reconstructing the image. Okay. So now let's do something a little bit harder. Okay. If I give you an unknown sinogram that looks like this. Okay. So if I give you, now let's kind of work the other way and go through the process of reconstructing this image. Okay. So this is a sinogram. Okay. And I just showed you how to create sinograms. Now how do we reconstruct the sinogram into using filtered back projection so that we can see the morphology of the object. Okay. Well, to do that, we use this iradon function. Okay. So the iradon function, okay, and I'll go ahead and do it and show you what that looks like. If I reconstruct that that sinogram, this is what it was. It was the Shep-Logan phantom. Okay. So you can see how that works. Now let's take a look at a larger study. So here I have, okay, here I have a study. This is a CT of someone's torso. Okay, look at all the sinograms, and I'll just scroll through them briefly. Think about it. Each one of those lines, okay, what are they? Those are objects inside the body, okay? And look at how they're producing these traces, these sine wave kind of looking things. That's the sinogram, okay? And look at this, okay? So I'm going through the different sinogram. This is what the raw image looks like, okay? And we have to reconstruct it in order for it to have any kind of clinical meaning for diagnostic purposes. So let's try reconstructing this. And you'll notice I'll have 460 of these sinograms. So I'm not going to do them all by hand. That would take a long time. Or I'm not going to do them all one at a time either. That would take a long time. Instead, I'm going to write an algorithm using a for loop that grabs the first image, reconstructs it, saves it, grabs the next image, the next sinogram, performs the filtered back projection, reconstructs it, saves it, and grabs the next one using a for loop. Okay. So if I come here, I'll show you the code that I've written. Okay. It's got an input path where I have all those sinograms. Okay. And then you'll see here I made this for loop. And this for loop is going to do exactly what I just said. It will take the first sinogram, reconstruct it through back projection, and save it. Take the next one, reconstruct it through back projection, save it. And then ultimately it's going to stack them all together, okay, in something called a hypercube that we can then scroll through. If you can imagine all those slices stacked on top of each other, and we could scroll through the z-axis, we could see what that would look like. So I'll go ahead and run this for loop. Let's see what I'm missing down here. To run this. Okay, so it brings up the sinogram first, then the reconstructed image. And like I said, every time it grabs one sinogram, reconstructs it. Grabs the next sinogram, reconstructs it. grabs the next sinogram, reconstructs it, okay? And you can actually see in the reconstructed image, this is the lower part of the torso. You can see these are the lungs, okay? You can see the lungs. You can see the chest, and it's going up the body. You can even see the aorta. The aorta is just in front of the spine. And this is, because I'm showing this live, it's going to take a really long time. So what I'm going to do is I'm going to abort this. Okay, so I'm going to press Control C. Okay, that aborted the operation, and instead I'm just going to have it not show me those. I'm going to comment out the figure IM show. Okay, I'm going to hide those and let it run, and it'll run faster. It'll run faster, okay? Even then, it's taking a little while to run. Well, let's give it a little bit of time. And then we will go through and cycle through that hypercube, okay? Let's check where we are. It's only on 82. We've got 400 to go. Maybe maybe it'll take too long. I'll cancel it, and I'll just show you one that I've already got done. Let's go over here. Let me pull up something to write on. And I just want to explain to you real quick what is a hypercube. Okay, so an image, a 2D image is something like this, right? Has rows and columns. It's a matrix, right? And like I was saying, I take the first one, reconstruct it, and then I stack them up next to each other, and I create something called a hypercube. Okay, something like this, where the next image gets placed right behind it right here. Okay, and the next image gets placed right behind it right here. And I keep stacking up all the images, and then I can cycle through these images and look through them. Okay, let me show you what that looks like. Okay, so we went through all the sinograms, reconstructed all the sinograms using the filtered back projection, and then we stack them all up next to each other so we can scroll through it. Okay, so let's see what that looks like. It takes a while for it to load. I'll go ahead and close Matlab, free up some resources on the computer. And as that's working, I want to bring up another concept. Okay, so again, you have rows or columns and rows, right? These are the columns. These are the rows, right? And this makes up the matrix of pixels, right? And so on one image, on a 2D image, you just have one pixel looks like this, right? But as you create this, as you start stacking them up, you start adding more. We create kind of a 3D volume, okay? So, and now we call it, instead of a pixel, we call it a voxel, okay? So now we have a voxel. Okay, so if we include the image, the stack of images behind it, okay, I get a hypercube. Okay, and each pixel is now called a voxel. Okay, and let's see if this. Okay, this has loaded now. Okay, so here's all the reconstructed images. Okay, so this is a CT scan of the torso starting about chest height. Okay, and let me move up. Okay, so I'm cycling through. I'm moving up. Okay, here you can see some ribs. These are the two lungs. Okay, this is a vertebrae. This is his airway. Okay, as I'm moving up, this is his collarbone. Okay, collarbone. And as I'm moving up, okay, this is again his airway in his throat. Okay, and as I move up, this is his jaw. This is his bottom jaw. Okay, there's his airway. There's his nose. There's his eyes. Okay, so again, we stacked them all up and created this hypercube, which they call a study. Okay, and then we're cycling through those images. Okay, so I'm just going through them like this. This is his head. Okay, there's his brain. You can see the ventricles inside the brain here. And going all the way to the top, you can see the crown of his head. This is the top of his head. It's the very top of his head. Okay. So I'm going to go back down. Okay. So you can see how we've taken all these projections at many different angles all the way around the body and created these sinograms and moved down the body by imaging through slices going down the body, and then reconstruct all of these sinograms and then stack them all up next to each other to create this study. Okay, so this is a CT scan. Okay, so this is a CT scan of just this guy's torso. So in a CT scan, if you break your foot, they're not going to image your whole body. They're just going to image your foot. So although they can image you can image the whole body. A lot of time, CT scans are just going to be the part that they're interested in. If they want to look at the head, they just image the head. If they want to look at the foot, they just image the foot. Okay, so this is here they just image the top of the torso and the head. Okay, so that's what that looks like. Okay, and remember, all of this comes from these sinograms. That all of this is what we just looked at, reconstructed. This is what a raw image looks like in a CT scan. Okay, and again, I'll remind you, this is the power of combining two important concepts of the hardware and the software, right? The software is the programming and the mathematics and the image processing. The hardware is the X-ray tube and the X-ray detectors and the design of the system. You need both, right? You need both in order to produce these images. Okay, so that's how a real sinogram looks like, and that's how you can reconstruct it. And let me now introduce you to mimics. Okay, so I'll open up mimics. And I'll just do a brief introduction. And like I said, what I'm going to do is I'm going to post a workbook online with step-by-step tutorials. and I'm gonna post a CT scan, okay, that for you to work through, okay, and follow step by step and go through it at your own pace. But just briefly, I'm just going to show you an introduction, okay? So this is Mimics. I've opened up Mimics. Now let me open up a study, okay? So I'm going to open up a CT scan of the head, so of the skull. Open up a CT scan of the skull. And remember, we have this hypercube, right? We have this um, study like this, right? Well, we can look at it, we can slice it and look at it different ways, okay? If we look at it from the front, uh, uh, that's what we call the axial view, okay? So that's this one here if we're looking at from the front, okay? But if you look at it from, you can look at it you can slice it in another way. So you can slice it like this and look at it in this plane, okay? And that would be the coronal view, or you could slice it in this other plane this way, okay, and look at it in this view, and this is what's called the sagittal view, okay? So, and it's got them labeled right here. So this is axial, this is coronal, this is sagittal, okay? So here's the axial view, and again, if I just go up and down, and this software syncs them. So anywhere I click on here, so let's say, for example, I'm going to go up, okay, to this guy's eyes. I'm going to go back down to his eyes. His eyes are right there, right? Those are his two eyes right there. If I click on one of the eyes, it will move to wherever I clicked on the other views, okay? So there's one eye. If I click in the middle, it's going to show me the middle, okay? But remember, these are just nothing but stacks of images. They're all stacked up on top of each other, okay? So I can cycle, I can move up, okay? So here I'm moving up. Okay, I can go to the top. This is the crown of his head. This is the top of his head. Okay, right here in the axial view. In the coronal view, you can see that I'm at the top here, and in the sagittal view, you can see that I'm in the middle here. Okay, so I'll just go back down somewhere in the middle, right about here, where his eyes are, maybe. There's his nose. Okay. So that's the way this is oriented, and you can scroll through this on the, for example, in the sagittal view. Over here, I can do the same thing. I can scroll to the left. If I want to go to the left, and I can scroll back to the right. I can scroll to the right. Okay, so I can slice this hypercube in different ways. Okay, so these are like looking at cross sections. Okay, of these images stacked up on top of each other. Okay.